Hi, I am Badrul. I will start the presentation with introduction. A typical biogas plant typically consists of four main units, which are pre-treatment unit, biogas digester unit, purification unit, and biogas utilization unit to process fresh pomade into biogas. Before pomade can be used as the feed in the biodigester unit, it will undergo some treatment process in the pre-treatment unit. Typically, open ponding systems are used for the treatment of pomade due to its lower operational cost and operational simplicity. Raw pomade will be supplied to the first section of the treatment system, which is fat pit. In this section, the remaining oil and grease in pomade will be collected. Meanwhile, pomade will then be passed to the cooling point to lower the temperature of the pomade, creating the optimal condition for anaerobic decomposition to occur.
My name is Gladys and I'll be explaining about the reactor system for the proposed biogas plant. After foam is treated, it will then be sent to the biodigester unit to undergo anaerobic digestion, which consists of four main stages. The first stage is hydrolysis, in which complex polymers such as carbohydrates, proteins, and fats are broken down to its monomers. In this project, carbohydrate will be considered as the main raw material. In second stage, the monomers will then be fermented and converted to metabolic intermediates such as alcohol, aldehydes, and volatile fatty acids, as well as some gases such as carbon dioxide and hydrogen. Meanwhile, in the third stage, which is acetogenesis, the product from the second stage will be converted to acetate, hydrogen, and carbon dioxide to be used later by the methanogens in the last stage. In stage 4, which is methanogenesis, the substrates earlier will then be converted into carbon dioxide and methane, which is the biogas that we want to retrieve. This is the proposed reactor system for the conversion of foam into biogas. Treated foam will then be added with water before it is fed to the reactor. We'll be using CSTR as our reactors as it is versatile and has lower operating costs compared to other type of reactors. In the first CSTR, it is assumed that only stage 2 occurs in the reactor. This is because since the composition provided in the problem statement is just carbohydrate, it is assumed that the carbohydrate already exists in its simplest form, which is glucose. In CSTR2, stage 3 and 4 will occur subsequently. In order to make sure that only stage 2 occurs at CSTR1, its pH value have to be maintained at around 5 to 5.5, while in CSTR2, the pH is maintained at 7 for stage 3 and 4 to occur. The reactor will be operating isothermally at temperature of 37 degrees Celsius and 1 atm with negligible pressure drop. At first reactor, reaction 1 and 3 will occur, which bring us to this overall chemical equation. The composition of the stream leaving the CSTR can be calculated by using stoichiometric table. Based on one of the articles, the acidogenic bioreactor typically runs for about 14 days. So by assuming the spacetime to be equal to 14 days, the volume of the reactor can be calculated as follows. In stage 3, reaction 2 and 3 will occur, and this is the overall chemical equation for stage 3. Similarly, the composition of the stream after it completed stage 3 can be calculated using the stoichiometric table. In stage 4, only reaction 1 will occur, and the composition of the stream leaving CSTR2 can also be calculated by using the stoichiometric table. Based on the same articles, the methanogenic bioreactor typically runs for about 21 days. So by assuming that the spacetime is equal to 21 days, the volume needed can be calculated as follows. Based on all the information that we have calculated, the overall yield of methane based on the amount of carbohydrate fed to the reactor can be calculated by using the formula as shown in the slides. The biogas produced will then be sent to purification unit to produce high purity biogas.
Hi, I'm Mindy, and now I'll be talking about the course CB2053, Process Modeling and Simulation. In this integrated project, we are requested to apply our knowledge learned from this course throughout the semester to firstly, to develop the dynamic mathematical models for the process of biogas production and to simulate a steady state reaction process using Aspen HYSYS. Following that, we are required to analyze deviation between the manual calculation and simulation, and lastly is to execute sensitivity analysis on reactor performances in HYSYS. Well, this is a very simple yet complete flow diagram of the biogas production reaction based on software HYSYS. And in this diagram, we have the components and the conditions in each stream. Right below the diagram is the reaction that takes part in each reactor, and beside the chemical formulas are the reaction rates. With these chemical formulas and the reaction rates together with the flow diagram, we can develop these dynamic mathematical models that are overall mass balance, component balance, and energy balance. Next, we are going to apply the knowledge and technique learned from the lab session to simulate this process in Aspen HYSYS. Same like the other simulations that we have done in class, it follows the sequence where firstly, we select the components, then we add the reactions. Following that, we'll go to the simulation tab and select the streams and unit operators. In this case, that is the CSTR, and then connect the streams together to ensure the flow. Next, we'll set the parameters such as the temperature, pressure, flow rate, or composition that we got from the previous chapter. The diagram over here is the simulation that our group has done in the HYSYS. The CSTR here appear to be in blue color, indicating that our simulation is successful, or else it would be yellowish color. After we are done with the simulations, we'll validate the simulation by comparing the values from manual calculations and simulations. The manual calculation is based on the component balance that we've developed earlier by using the data from the previous chapter. Then, we'll compare these values with the one generated from the HYSYS. So from this table, we can see that the percentage error for each component between the manual calculations and the HYSYS simulation actually exceeded the accepted range. Well, this is probably because that in the previous chapter we assumed negligible vapor pressure, while in HYSYS vapor pressure is considered. And secondly, in the previous chapter, we also assumed no volume expansion to simplify the calculations, while in HYSYS volume expansion is considered. Lastly, is that in the previous chapter we assumed that the system is isothermal, while in HYSYS the system is actually non-isothermal, and this explains why the values deviate so much. Next up, we'll evaluate the sensitivity analysis on reactor performances in HYSYS by firstly changing the feed flow rate. So in this graph, we can conclude that when the feed flow rate increases, the conversion in CSTR1 increases, but in CSTR2 the conversion does not differ much. Next, if we change the inlet temperature, we can see that the conversion in CSTR1 and CSTR2 both decreases. Lastly, we evaluate the sensitivity analysis on reactor performances in HYSYS by changing the pressure. So from this graph, we can see that when we increase the inlet pressure, the conversion at CSTR1 and CSTR2 does not really change much with the increase of the pressure. So we can say that in our simulation, the conversion at CSTR1 and CSTR2 are independent of the inlet pressure. That is all for this course. Thank you.
Hi, my name is Deborah, and now I'm going to present on the chapter of separation process 2. In these sessions, I will focus on the design of downstream separation process systems for removal of contaminants from the raw biogas. We need to identify what are the unwanted contaminants that have to be removed from the biogas. Here are the composition of biogas, and among all these compositions, we need to remove carbon dioxide because it will decrease the energetic content of biogas. Knowing that, it's important to remove the water vapor because it will react with the hydrogen sulfide and the carbon dioxide to form different acids, and this will lead to corrosions. Besides, we need to remove the hydrogen sulfide because it will provoke acid corrosions on the equipment and machine. Basically, there are two separation units in our design, and the first one is silica gel packed bed absorber, and the second one is the amine-based biogas scrubber. By using silica gel packed bed absorber, we are going to remove the water vapor. The raw biogas is fed into the absorber, and when it flows through the silica gel bed, it gives out moisture to it. The type of absorptions that involve are the physical solutions, whereby the water vapor is physically held onto the surface of the silica gel by the dispersion forces and polar forces. Once the silica gel is saturated with the moisture, the bed is heated to add the thermal energy that drives the regeneration of the silica gel. The thermal energy will push the moistures from the silica gel, and after the silica gel is completely regenerated, they will return to its initial dry weight and can be reused. The second separation unit is the amine-based biogas scrubbers. After the water vapor is removed from the biogas, the treated biogas enters the adsorber, and the MES solution will absorb the hydrogen sulfide and the carbon dioxide from the biogas. The saturated MES solution is going to pass through the dissolver. In the dissolver, the preheated saturated amine solution will fall downwards due to the gravity, while the stain will move in counterflow due to the pressure difference. The saturated strains is generated to heat the amines by direct mixing with the stains in the dissolver. At the same time, the hydrogen sulfide and the carbon dioxide are dissolved and released. The regenerated MES solution is entering back to the adsorber. It needs to be cooled down first. Therefore, there's a counterflow heat exchangers passed between the regenerated and the saturated MES solutions. Also, the condenser will help to further cool down the regenerated MES solutions, and now the solutions can be reused. At last, the treated biogas will pass through the water wash scrubber, whereby the amine traces are removed. And last, we can get the purified biogas with a high concentration of methane.